Hi, in this video we're going to have another look at these LED strips. So I did take one apart a bit further. I managed to get the lenses off quite cleanly. So I've taken a photo so that we can have a look on camera at what's going on. But basically what they've done is exactly what I was thinking that they wouldn't do, and that is they have one constant current switch mode regulator, and then they've got all of these LEDs in series, which I'll explain how they've done that in a moment. And then they've just got transistors that short out the various colours so that you can individually control them. So this is what they have on the PCB. They've got this constant current regulator, they've got all of the LEDs in series, a current sensing resistor for feedback, we've got the microcontroller, we've got the two transceivers for receiving and sending out the DMX512, and then we've got a 7805 regulator. And what they've done is they've got some transistors which are basically shorting out each of the channels. But what confused me in the original video was that if you add up the forward voltage of all of these LEDs together, it adds up to more than 24 volts. So you've probably got 10.5 volts here, 10.5 volts here, which is already at 21 then. And then the LEDs for the red are probably going to be between 6 and 6.5 volts. So we're already getting close to 28 volts. And this regulator, it was definitely operating as a buck regulator, so it wasn't boosting the voltage up. So we'll have a look on the scope shortly at what they're doing, but it is quite fascinating. I suppose it's quite obvious when you see what they're doing. But there is an application note for this buck regulator, the L5970D, and it tells you how to drive LEDs with this regulator to use it as a constant current regulator. So what it involves is just changing the feedback network here to monitor the voltage across a current sense resistor. So instead of having this feedback network monitoring the output voltage, you're just monitoring the current that's going through the LED. And because this regulator has a switching frequency of 250 kilohertz, and in this example they don't recommend using any output capacitance, it means that basically it can respond to the LEDs being PWM'd very quickly. So within one cycle, more or less, you're able to adjust the output voltage so that you maintain that set current through the LEDs. And then what they have on the schematic is just these PNP transistors which are shorting out the LEDs. At this end it's floating up near 24 volts, and again for the green it's getting close to that, so they have to have some interface electronics here so that you can drive the base appropriately for this transistor. And then obviously at the red end you can, it's got an open collector type output here on the microcontroller. I think there is a pull-up resistor here, but it does mean that you can drive it directly from the microcontroller. And then if we have a look at the picture of the PCB, you can sort of see all of that in action. So we've got the microcontroller here, we've got the crystal as before, and then we've got these transistors here, Q1, Q2 and Q3. This one's for the blue channel, you can see that going into the blue LED. We've got Q2 for the green LED and Q3 for the red LED. And then there's this sort of cluster of additional components here, and that does form these two drivers here. So we've got what appear to be a couple of dual bipolar transistors in one package, and that's doing sort of the level translation so that you can drive the base appropriately on these transistors. And then we've got the current regulator, which if you trace out all of these resistors is exactly this circuit shown here, only the feedback resistor, they've used a 0.33 ohm resistor here to give approximately 350 milliamps. They've changed some of the resistor values here, and that means that you're almost driving it at 780 milliamps. So let's have a look at the scope. What I've done is I've sort of pulled all of the transistor drive points off with some leads and connected them to the oscilloscope, and we can have a look in a moment at controlling the LEDs and see what that does to the waveforms. So what we have on the oscilloscope is the DC to DC converter output at the bottom, and then we've got the red, green and blue channels at the top, and this is the output from the microcontroller to those transistors. So if we turn up the red channel very slightly, what we see is a whole load of pulsars here, as you would expect for a PWM waveform. And if we zoom in very closely, what you can see is that that DC to DC converter responds to the change in, well, the extra demanding current and the change in forward voltage that it's seeing, and responds within about 10 microseconds. So that's well within the switching frequency of 250 kilohertz, and you can see that's quite happy. Now, what it does that's fairly interesting is, instead of doing pure pulse width modulation that you would normally do, which is where you just increase the duration that the LED is on for the very lowest brightnesses, what it actually ends up doing is adding pulses of that similar width. So I'm just increasing the brightness here, and what we end up seeing, if we zoom out, is more and more of those pulses being added in as we increase the brightness. And then once we get to around that point, if I zoom back in again, if we increase the brightness, you can now start to see the duty cycle increase more or less in the traditional way. And then when we get to full brightness, you can see actually it's only on for around 2/3 of the maximum time. So I did say that the constant current driver can drive 780 milliamps through these LEDs, but we don't actually see that full current going through them. And yeah, that's part and parcel of it not being able to drive these LEDs, or purposely not driving these LEDs at 100% duty cycle. Right, so I've just forced the trigger here, and what you can see is that the LEDs aren't ever actually on all at the same time, and that's because if you had all of the LEDs on at the same time, the forward voltage, as I explained before, would be greater than the 24 volts. So what they're doing is, for example, when you want all of these on at 100%, the actual driven current through them is 780 milliamps, but because they're only on for 2/3 of the time, it's only 2/3 of that value that the LEDs see on average. So what they're doing is they sort of got the blue and the green on together, then they've got the red and the green on together, and then they've got the red and the blue on together. The peak current through that is 780 milliamps, but each bank of LEDs only sees 2/3 of that. And also the side effect is that yeah, because there's only two banks on at the same time, the overall voltage is below the 24 volts that's incoming. So you can see it's floating somewhere around 19 volts, similar to what we measured before. There's some very slight differences on the waveform because of the different forward voltages of the banks of LEDs. And then if we turn off the red LEDs, you can see the waveform for driving the green and blue is identical, but the output voltage from the DC to DC converter has changed. So instead of it all being up here, we've got this period where the red LEDs was on, so it's again it's a 2/3 of the total period is lower by the forward voltage of those red LEDs. So you can see now it's floating at around that's about 12 volts, something like that, which is the forward voltage of the blue LEDs here and the green LEDs here. So yeah, I thought that was quite interesting. It makes complete sense when you think about it, but yeah, just measuring with the multimeter, it made no sense whatsoever. We did need to look at the waveforms. So I did find these waveforms quite interesting for how they're driving the LEDs, because if you use the PWM generator on your microcontroller, you're just going to get these basic waveforms where you have a fixed point here, a fixed point here, and a fixed point here, and each of these is your period. And if you want it on for 10%, you turn it on for 10% of that period and then leave it off for the remainder of the time, and then again on again and then off for the rest of the time. And then if you wanted 50%, you just increase that time that it's on and correspondingly reduce the amount of time that the output's turned off for. But another way of achieving that 50% is by having it on for only the same amount of time, but do that 5 times in each period. Or another way would be to have it on for an equivalent of 10 and then 20 and 20, and that's your 50%, and then you start again here. And you can see on these waveforms that's exactly what they're doing. They're mixing some of these pulse widths, which I'm not sure whether that's because of a limitation of the microcontroller that they're using on this PCB, or whether it's to try and reduce some of the flicker that you might see, because when you start doing this, you're changing your PWM frequency, and in the case of mixing different pulse widths, you're getting quite a varied range of frequencies, which means that you don't have a fixed tone at whatever frequency that you're PWMing at. But I think on the camera you can still see these are a little bit flickery sometimes, so if we look at this green, you can see there's an area here where it flickers and then it stops flickering, and I think that's just how they're altering these PWM waveforms. But anyway, I hope that's cleared things up for you. If you've got any questions or suggestions, leave them in the comments below. Don't forget to click the bell button if you want to be alerted of the next video that I upload. But until next time, thanks for watching.